Will you sit with me one last time? This is the last video. Congratulations for watching all the videos. Did you watch all the videos? I don't know. I made all the videos. Congratulations to me, at least. The last video is about using the integral to find areas of various things. Various areas, all right? I have said many times that the integral, from a to b, f of x dx, this is the area under the curve, right? So if you want to find the area of something, you just do the integral, okay? There are some cases in which it's not quite that simple. This is the area under the curve, but it carries with it a sign. We talked about this at least once before. If you have area below the x-axis, that counts as negative area. So if you have a function that, say, does like this, and you find the integral from here to here, say that. What if the picture looks like that, where the interval from a to b has this weird shape along the graph? When you do this integral, this counts as positive area, and this counts as negative area. Now, there's no real such thing as negative area in reality, but I'm just saying when you do the integral, it's going to measure this area as a positive number and measure this area as a negative number. And if you do the whole integral in an example like this, there will be some amount of cancellation. Like part of this, which is a large positive number, will get subtracted away by part of this, which is sort of a small negative number. All right? And so, what I'm trying to say here is the integral from a to b is not actually equal to this shaded area. It's sort of this one minus that one in this example, because that one's going to count as negative. All right? This is the kind of subtlety that I want to talk about today. Another subtlety is sometimes you want to find area even though it's not obvious how to set the integral up even in the first place. Let's do an example like that. Find the area bounded by the x-axis and this function, y equals x squared minus 3x. All right? The area is going to be the integral of something. It's the definite integral of x squared minus 3x dx. The problem is, what are you going to put here and here? All right? I didn't tell you what to put here and here. It is a fact, though, that this graph, it looks like, you can graph this on your calculator or something, it looks sort of like that. So the area I'm talking about is this, right? But where are these 2 points? These are the 2 points that you need to use for the a and the b, and I didn't tell you what they are. How could you figure out what they are? Well, in a problem like this, what you got to do is find these points. They are the x-intercepts. So we need to find the x-intercepts. All right, that's what will allow us to figure out what we're going to use for the a and the b in this problem. Now, I showed you this picture, but you can find the x-intercepts even without looking at the picture, right? How you find the x-intercepts, you set y equal to 0, because these are the points where the y value is 0, and then solve for x. Let's see if we can do that. Y was x squared minus 3x. I'm going to set y equals 0 and solve for x. So 0 equals x squared minus 3x. How do you solve this? This is a quadratic over here. You could use the quadratic formula, or I prefer to factor if I can. This is x times x minus 3. You break it up, right? X equals 0, x minus 3 equals 0. And then, so x equals 0 and x equal 3. All right, those are my 2 points, 0 and 3. So then the area is integral 0 to 3 of this function. And do you know how to do this integral? Yeah, this is an easy one. It doesn't need a u substitution or anything. It's just a polynomial. So I go x squared becomes 1/3 x cubed minus 3/2 x squared. And I plug 0 and 3. And you plug them in. 1/3 times 3 cubed minus 3/2 times 3 squared. I went through here and plugged 3 in for x. Now I go minus, go through here and plug 0 in for x. Actually, it will all end up being 0. I'll write it out anyway, just so everybody knows what I'm doing. All right, and that's the answer. This is the area between the x-axis and that curve. Sometimes you got to figure out the A and the B all by yourself. You can do it. Let's try this one. Find the shaded area of this guy right here. Okay, here's where we're going to have to grapple with the issue of some things being measured as negative versus some things being measured as positive. So let me just start off by saying you cannot just do integral 0 to 2 of x squared minus 1 dx. All right, if you do that, it's going to measure the area all the way across. It's going to count this one as negative and count this one as positive, and it's going to try to like combine them together. This one will cancel parts of that one, and the answer you get will be too small, right? Really what I want is the total area of this shaded region. You cannot measure the integral all the way from 0 to 2. What you got to do is break it up. You have to do the integral from 0 to 1 first, and then the integral from 1 to 2. So we do the integral 0 to 1 of this function, x squared minus 1 dx, and the integral 1 to 2 of this function, x squared minus 1 dx. And when you do this, if you do it correctly, you will find this one will be negative, and this one will be positive. That's because, like I said, this one is area beneath the axis, and so when you do this integral, you'll get a negative number. This one is area above the axis, and so when you do this integral, you get a positive number. To get the true value of the whole shaded area, you've got to add those numbers together, ignoring the fact that this is negative. So I'm going to say you're just going to make both of them positive, right? This one we know will be positive. The negative one, you're going to just make it positive and then add them together. That will give you the total area of the shaded regions. Let's see if we can do it. I don't really need the picture anymore. How do we do this integral? This is not a hard integral to do. It's going to be 1/3 x cubed minus x from 0 to 1. I plug in 1 first. 1/3 times 1 cubed minus 1. Subtract. Plug in 0. 1/3 times 0 cubed minus 0. All right. Now, ordinarily, I wouldn't try to simplify this, but remember what I said, our procedure. Find out what this number is, make it positive, so this will be negative, make it positive, and then add it to the other one. I'm going to simplify this entirely here. 1 cubed is 1, so this is 1/3 minus 1, and all of that is 0. This is 1/3 minus 1 is negative 2/3, all right? So that means on the picture, we have these two parts. This one apparently has area equal 2/3, right? When I did the integral, it came out as negative. That's just because it's below the y-axis. But the actual area, which is never negative, the area is always positive, the area is 2/3. Okay, what's the area of the other part? And then I'm going to add them together. The area of the other part shall be just the integral from 1 to 2 of the same function. And this, I have the same antiderivative. 1/3 x cubed minus x, plugging in 1 and 2. All right, plug in the 2, I get 2 cubed minus 2, subtract, plug in the 1. 1/3 times 1 cubed minus 1. All right, and this also I'm going to simplify because I intend to add it together with that. So I have 1/3, 2 cubed is 8, so this is 8/3 minus 2 minus, and then this actually is the same as that. It's negative 2/3 in there. Can I add these together? You could use a calculator if you want to, but this is not so hard. I got thirds. This is all about thirds. Make a common denominator, would you? 8/3 minus 6/3 plus 2/3. Add them up for a total of 4/3, I believe. So that means this area here is 4/3. And so the total area is 2/3 from the first part plus 4/3 from the second part, which is 6/3, which is 2. That's the answer. This is how you do it. You got to break it up into pieces, make them all positive, and then add them together. Just one more, then we'll be done for good. Find the area between the x-axis and this line, y equals 2x minus 14, on the interval 6 to 10. So that means on the picture, you know, this is a line, so maybe it looks like that, and I go from 6 to 10, and I find this area, right? This is not hard. If this is really what the picture looks like, then you would just do the integral from 6 to 10 of this function and leave it at that. All right. What could be slightly tricky about this is, so that might be what the picture looks like. That would be an easy situation. What if, though, instead of that, the picture looked like this? This is the worst case scenario. The picture looked like that, in which case the area is going to be like this, split into 2 bits, right? Does that happen, or does it look like that? We need to do, like we did in that first one, find any x-intercepts and see if it actually crosses the x-axis. If it does cross the x-axis, we're going to have to split up the integral, like we just did, into 2 parts, right? One being 6 going up to wherever this point is, and the other point, and then the other being this point up to 10. Okay, so let's see if there are any x-intercepts. And if they lie between 6 and 10, then we got some work to do. X-intercepts, remember we set y equals 0 and solve for x. So it's going to be 2x minus 14 equals 0. Solve for x, and 2x equals 14. X equals 7, right? Okay, so that intersection, actually it is in between 6 and 10. The picture truly does look like 6, 10. It actually goes through here at 7. And the line, I know it happens... I happen to know it goes up because the slope is positive too. So it's like that, right? So what I'm talking about is one small negative bit area and then one larger positive bit area. We're going to have to do like we just did in the other problem. Break up the integral into 2 parts, make each part positive, and add them together. Let's do it. So for this little piece in the negative direction, I'm going to have to do the integral 6 to 7 of that function, 2x minus 14 dx. Let's do it. Take the antiderivative. I get 2x becomes x squared, minus 14 becomes minus 14x. And then I put 0 and 7. Plug them in. Not 0 and 7, 6 and 7, right? Plug them in. 7 squared minus 14 times 7 minus 6 squared minus 14 times 6, right? I plugged this into my calculator. You could probably do this by hand, but I got a -1 for this, all right? Seems about right. I was expecting the area to be fairly small, but negative. Okay, -1. So the true area right there is 1, right? When I did the integral, it came out as negative. That's just because it's below the y-axis, below the x-axis. But its actual area is 1. Okay, now we got to do the other one, and we're going to add them together. The other one is integral 7 to 10 of, same business, 2x minus 14 dx. I get the same antiderivative, which is x squared minus 14x. I plug in 7 and 10. Okay, plug them in. 10 squared minus 14 times 10 minus 7 squared minus 14 times 7. Put that in your calculator and smoke it. I got 9 from that one. All right, so that means this area here is 9. So what's my final answer? Maybe I'll just squeeze it over here. My final answer is I add them together. So the total area is 9 plus 1 equals 10. There you go. And I think we're done. Thank you very much. Why must you play me like this?